All right, I think our webinar is officially started. I can see some attendees joining us already. We promised to give a couple of seconds for everyone to get the chance to enter the webinar room. So we'll just wait half a minute here and then we'll kick off with the introduction. Yes, I think meanwhile I can start sharing my screen so that everybody knows which webinar they are actually attending. And maybe as we wait for participants, I can just kick off this session with a brief introduction. So I will officially welcome everyone to this session arranged by 4 EU-funded projects. So we have speakers and panelists today from Ocean Ice, from OBPS for ClimTip, and from TipESM, presenting and discussing on the ocean climate nexus and the importance of ocean observations for our knowledge on tipping points. My name is Justyna Bekier. I work at the Danish Meteorological Institute and I'm a project manager for 2 of these projects. I work with OBPS and with TipESM. So first of all, just to start with, why did we even arrange this session with 4 different EU projects? Well, in all of these projects, we operate in some way at the ocean climate nexus. We know that ocean and climate are inextricably linked, and the projects that we'll present here today contribute to our understanding of these links between ocean and climate. And all of our projects touch upon the science on tipping points, either by working with simulations of tipping points or by providing inputs to these simulations. And when we talk about tipping points today, we mean the critical thresholds in the Earth systems, beyond which the system reorganizes, often abruptly or irreversibly. And so as we work on tipping points, we realize that this knowledge on tipping points is still limited. That applies also to ocean tipping points. And so far, climate models only partially represent the range of processes and feedbacks in the Earth system, meaning that there is a need for improved ocean observation to improve these climate models. So in today's workshop, we will have speakers from TipESM, ClimTip, OBPS and Ocean Ice, as I mentioned, presenting and discussing these different aspects of the ocean climate nexus. And so to give a bit of background on these 4 projects, we have TipESM and ClimTip that use Earth system models to study tipping points, also tipping points like the meridional overturning circulation or the subpolar gyre. So ocean data is extremely important to them. We have Ocean Ice that provides novel in situ observations to Earth system models and examines the sensitivity and tipping points of modeled ocean ice sheet coupling. And we'll learn more about that in one of the coming presentations. And then we also have OBPS that provides improvements of the essential ocean variables and essential climate variables to reduce the uncertainty in Earth system models. And we actually had a session with OBPS yesterday at this Ocean Best Practices System workshop. So we discussed that in more detail. And if you're interested in that aspect, I would encourage you to check the YouTube recording of that session. And today we'll address 2 themes that relate to ocean science. On the more technical side, we'll discuss the development of common protocols, improving observational estimates, and sharing of methods, standards, and results across the scientific community, because all of this can support better predictability of tipping points. And then more broadly, we'll also touch upon the theme on science development, where best practices can support development of climate ocean science that addresses user needs effectively and ethically. So altogether, we'll address the question of how can ocean best practices help in understanding tipping points. And if you're interested in our projects beyond this session, I encourage you to visit the respective websites where you can also connect to our social media and check the content related to our projects. And this is the detailed agenda for today. So we've gone now through this brief presentation, and now we'll start with 5 short presentations from our speakers. We'll have Didier Svingadou from University of Bordeaux introducing the tipping points topic and what are the challenges. We'll have Xavier Rodo from ISG Global, the Barcelona Institute of Global Health, talking about improving the predictability of climate tipping points with an enhanced ocean observing system. Then we'll welcome Andrew Myers from the British Antarctic Survey, introducing novel ocean observations, followed by a presentation from Shalmar Hatun from Houstovan in Faroe Islands, introducing some knowledge on the AMOC transport observations. And then we have Paula Salge from Collab Plus Atlantic, talking about from climate science to decision making. And then we'll have half an hour to take some questions. If you have any questions in the meantime, please address them in the Q&A panel. Otherwise, the panel discussion where we'll have Ana Oliveira from Collab Plus Atlantic, we'll have Didier Svingadou, we have Juliette Mignot from Institute of Research for Development, and Laura Jackson from the British Met Office. So I would like to welcome all of the speakers and the panelists, and then without further ado, I will let Didier start and share his screen.
Okay, thank you. So, second. Okay. Can you see my, no, not yet. Can you see my screen?
Yes, that's perfect. Thank you.
Okay. Okay, perfect. So, hello everybody. So, yeah, my name is Didier Svingadou. So, I'm from CNRS, based at University of Bordeaux in France. And I'm here as a, let's say, a work package leader of the EU TipESM project. And I will provide a few insights concerning the tipping points and the main challenges that I can see. So that's mainly my point of view, I should say. I hope it is shared by some colleagues. And so I will present the main challenges concerning the ocean tipping points and where we might need some observation. So TipESM is mainly composed of a bunch of modelers. So we are not the main expert in observation, but we know that there is a lot of uncertainty in models. And what I will talk about today is mainly about the large-scale ocean circulation, so the tipping points related to this circulation, and most importantly, I will talk about what we call the AMOC, so this transport of warm water from the southern hemisphere towards the northern hemisphere, where it is reaching the convection sites, where it is sinking. So these convection sites are located in the subpolar gyre and the Nordic seas, and this is a crucial processes to form deep water. And in fact, those convection sites might be at risk when the climate will change. There are other convection sites in the Southern Ocean, but I will not talk about them today. So I will mainly focus on the AMOC, which is believed to be possibly bistable with potential irreversibility, and this irreversibility and the risk of a tipping point is mainly related to positive feedback due to the salt advection. In fact, if the AMOC weakens, less salt is transported in this high latitude, weakening further the convection and so on. And so this feedback, this salt advection feedback, can be seen as quite local, but it can also concern most of the Atlantic Ocean and its linkages with the other ocean. And in fact, it's mainly a question of time scale concerning what we are looking at. Why do we care about this large-scale circulation? It's because its impact can be huge and explain a large amount of uncertainty in the future climate, as shown in this picture from IPCC SROC report. There might be, in case of a substantial weakening, which means about 50% weakening, quite some impact in the over Europe, which are quite well known, but it's not the only impacts. In fact, you also have impact in the West Africa, which is highly inhabited, related to the change in the monsoon system, and the same can be true through teleconnection in the Asia, and also in South America, with potential impact on Amazon rainforest. And this is concerning physical, biological, and human systems. So the big question is, what about the AMOC fate in the future during this century? According to IPCC, it will very likely weaken, but by how much is another question. And if we look the latest generation of model, we obtain something like 30% of reduction for a medium emission scenario. But you can see that the uncertainty is huge, in fact. And that's where observation can be useful, because in fact you can use observation to try to reduce uncertainty, but what is called observational constraint, used in latest IPCC report to constrain, in fact, the global warming mainly. And that's what we are developing within TipESM, and I can show you here some preliminary results using what we call the multivariate approach, using different sectors and variables that might explain the spread among the different models. And if we use all those sectors, we end up with this estimate. And to summarize, what I can show is that with this observation-based estimate and concerning the bias of the model, we end up with a stronger reduction and with also a smaller uncertainty. And we can also attribute which process or which variable is driving such an estimate. And it's mainly the South Atlantic SSS, which might be related to some recent paper highlighting that, in fact, the transport of salinity there might be very important for the AMOC fate and the proximity of a tipping point. What should be kept in mind is that in all those projections from state-of-the-art models, in fact, Greenland melting is usually not included. While we know that Greenland is melting at a faster and faster rate at the moment, and it might have some impact on the AMOC. And what we've shown also in another project, a recent EU project, Blue Action, we've shown that, in fact, depending on the resolution, the impact might be very different. If you consider what I call here low resolution, but which are kind of CMIPS models, so state-of-the-art models used by IPCC, or very high resolution, you can see that the recent meltwater from Greenland can have very different impact. And here on this scheme, I'm explaining why. Here you have a scheme of low resolution and high resolution. And in fact, when Greenland is melting, you are changing the coastal current, which are very seen in reality and in high resolution model, quite large, wide in the low resolution model. This meltwater is weakening, freshening the water there. But in the high resolution, since the current are thinner, the freshening is higher. And another key ingredient is the fact that you have lateral mixing mainly through eddies, which are quite homogeneous in low resolution models through parametrization, while in high resolution you have eddy resolved, and you have in particular this region where you have a lot of eddies at the tip of Greenland, and as a consequence, the freshwater coming from Greenland can reach more easily this convection side, leading to a stronger reduction. And I'm talking here about 1 order of magnitude stronger reduction. So that's something that is not considered and might be very important. How well do we observe this transport of salinity is a crucial question maybe for the observation. Another tipping point is related more precisely to the subpolar gyre, and we've shown in other project, EU project Embrace, that this subpart of the MOC might tip more rapidly with a collapse of convection than can occur in just 10 years, so very rapidly, and we can see this there with different models. One model where there is no tipping, another model where you have a tipping of the SPG with a strong reduction of temperature related mainly to convection collapse and not only the MOC. And in fact, once again, the key ingredient is a positive feedback related to transport of salinity. And here, in fact, it's on a shorter space frame, which explains why it's occurring faster. How well this transport is represented, once again, is a key aspect in my view. Can we have any early warning of such a collapse? That's also a crucial question. What we propose for the moment is using stratification, so the change of density with depth. And we can see here that if you define a critical stratification in models, you can see that the recent observations are within the overlap of this critical stratification. So we need to make some progress on the estimate of this critical stratification just before the collapse. And what we can say is recent observations from salinity are not showing any clear trend. And we can also see that the remote sensing system are showing quite consistency now with the in situ observation. So last but not least, in work package 4 from TipESM, we are searching for new early warning indicators. Also by considering the three-dimensional pattern of some precursors, some physical precursors just before an SPG collapse. And I can say that we are also planning to compile a set of early warning indicators, mainly based on these physical precursors, and a register will be delivered in 2026, which might include observational requirements, and we might be happy to discuss with the other project to have a better estimate of that. So I can conclude by saying that this EU project is mainly using Earth system models to better evaluate the risk of tipping event in the near future. And we also plan to try to constrain a bit future projection using observation. So that's why it's very important. Develop early warning system, once again, using observation. So we are really keen to learn more about the new observation and what is might be useful to observe. And on this point, I think that the transport of salinity advection is really crucial to estimate, to have a better understanding of the tipping points. And also conserve existing measurement, please, because that's very key. So thanks a lot.
Thank you, Didier, for this presentation. Wonderful. If there are any questions to Didier, I would encourage to add them in the Q&A panel. And I'll now invite Xavier Rodo to share his screen. We can see your screen, but you're muted, so we can't hear you yet.
Okay, now
Brilliant.
I
Thank you.
hear. Okay. Thank you very much for the invitation, and I will briefly also report on why ocean observations are important for the work we are doing in TipESM. As already, sorry, I think it's my screen is blocked. Wow. So I have blocking in my Mac. Anyhow, I'm in, let's see if it works. If not, I will have to reinitiate. So yeah, I'm working on ecosystems. No, it doesn't. Well, ecosystems modeling and health systems modeling in relation to the occurrence of tipping points in the climate system. In the project with the idea of seeing whether these natural and human systems will also undergo dramatic changes or even tipping dynamics. So let's see if I can stop share and sorry again, I'll try. Okay, let's try this.
No, it doesn't share my screen
Oh,
presentation.
yeah, okay. Wait. Okay, so.
Are you able to see it now?
Yes, but I have a problem. I don't know, my laptop. It's not, I only see part of, okay. Now I see the screen. Okay, you can, well, not skip this, just very briefly. We are essentially, and I'm going to talk about the Amazon dieback, so the mesotropical rainforest, as one of the tipping elements which might give rise to zoonotic diseases, such as, for instance, we've seen in other regions with regard to the last pandemic. So in our case, we are interested in understanding the role of El Niño sound oscillation also in this amplification of this vegetational response, and we are working on both El Niño models and also vegetation models in our system models. Okay, next, please. Yeah, a couple of weeks ago, you might have read this paper appearing in Science by Sonnet Alter, in which I would say that maybe for the first time there was a direct link between the occurrence of El Niño sound oscillation and biodiversity collapse. So this was at the transition period between the Permian and the Triassic, and essentially what they describe is a decrease in the SST gradient in what was Pantalacia, in an area where it can be an analog of the Niño 3.4 region. So essentially, this is highlighted in this plot at the left-hand side as just the decrease of the SST gradient, and in the third panel there is the collapse of the vegetation, and this tend to happen quite in synchrony and in advance of the MOC collapse. And one of the patterns, not yet, thank you. One of the patterns of El Niño that we are studying is the potential permanent El Niño conditions. And in that study, what they reported is that this is not a situation that tends to happen. So you know that the future of El Niño sound oscillation is a little bit under debate. And instead, in this study, essentially what's explained is an amplification with longer lasting, stronger El Niño and La Niña events. So this increase in variability, and with these events lasting longer. And the situations which are analog to the moment we are now would be in this Transindian period between 400 and something ppms and the 800 over 800. And we can see that also in the panel in the left, that at some time between these two states, there is this kind of massive effect on the Amazon rainforest. Next, please. Okay, so we are, as part of TipESM, also analyzing as benchmark conditions, CMIP6 simulations, and how El Niño and La Niña will change in the future. Essentially, the dark bars indicate, both for El Niño in red and La Niña in blue, that there will be noticeably more of the two phases of the ENSO event. So there will be more events in the future. And when we composite the responses in rainfall and temperature, which are these other panels right here, what we see in relation to the Amazonian region essentially is a strong decrease in rainfall in the Nordeste of the area, in that might go up to the southwest. That's exactly areas where we are seeing recurrent floods and droughts, also as a response of the triple dip La Niña, of the enhanced El Niño events occurring in the last years. And also there is this dramatic increase in temperature, over 6 degrees, and even higher in certain regions also of the system, which, next slide, please. Yeah, some recent studies have attributed to those similar situations the potential collapse of the rainforest, such as in this study by Nian. We see in the third row with global warming level similar to the one we are now undergoing, we see these red points indicate the transition between rainforest to savanna, and this massive collapse that in the blue line in the right-hand side plot indicate a really nearby decrease and dieback of this forested land. No? Next, please. So what effects might this have on the spillover of zoonotic diseases, which are the ones that the human society might be threatening more because of the risk of pandemics? We see that most of the major, for instance, vector-borne diseases are concentrated in these large biodiversity hotspots, and in particular in the Amazon is in the place where most of them concentrate because of this largest biodiversity. So we were studying how this potential spillover was now taking place, if that were the case, and that's an example with a parasitic disease, that's a cestode that infects the liver of the rodents that then are ingested by the vertebrate hosts, and with which humans can be in touch either by consumption of the animal remains or because they came in touch with the feces of the domestic dogs. Next, please. So curiously, when we try to build a model describing how this process takes place, and you can see, for instance, because there is a rich database of both the rodents and the predators all around Panamazonia, so we can construct these ecological niche models and then try to see what drives the animal model and what drives the human model. So this interaction with the humans, between humans and animals. And in the animal model, it's striking to see that the first variable driving the model is the quasi-biennial component of temperature. And when we see the shape, which is this plot right here, we see that the model tends to favor lower values of this variable, so it tends to favor stability. So more stability means enhanced populations of these animals. And instead, when we try to combine this with the human interaction, because there is a lot of subsistence hunting, we see that after population, the other variable that drives the model is the quasi-quadrennial component of ENSO, and of temperature, that's strongly linked to ENSO. And we see that when these values are larger, we have more impact on the human model. So more variability means more spillover, more contact with the rodent and the disease as in turn. Okay, next model, next. So, well, we can skip that. Essentially, that reflects the signatures of El Niño Savan oscillation on this same region. And we see that they coincide, obviously, with the quasi-biennial and quasi-quadrennial signatures, and they are quite constant throughout the record. Next slide. And for this also, as I said, we are working in parallel on the understanding of El Niño Savan oscillation origin and predictability. And we've been developing a long lead statistical model that now it's being added to the long lead forecasting plume, and that uses ocean observations in different regions in the tropical West Pacific and South Pacific Ocean. And essentially what these indicate, and that's maybe the relevant plot right here, this third plot in the middle, is that after the ejection of the TOGA program in the Pacific, and there was an increase in the skill, so a decrease in the error of the model, so that the model benefits a lot for the enhancement and the availability of surface and subsurface observations. So next slide. So the model uses predictors that are up to 500 meters depth, and the skill of the model benefits a lot of this addition of data. So next slide. And we can see in the table how for different events, the bold values indicate different layers of the ocean that in different regions, because there is a lot of nonlinear behavior and development of these events. The different areas contribute differently to the development of different El Niño events. At the end of the day, we use these to feed and nudge disease models that use these observations as sources of skill. In this case, I have no time, but in this case, this is for dengue prediction in Ecuador and Venezuela. And we can see how the skill is benefited for the addition of these variables. And then the last slide, please. It has to do with a similar system for malaria prediction in East African highlands, and where the different and non-linear information regarding the state of El Nino and the North Pacific Ocean really helps much in predictability of falciparum malaria in North African highlands. So yeah, I think that's the last slide is the last slide. And yeah, I thank you for your attention, and I apologize for the problems with the presentation.
No worries at all, and thank you, Xavier, for this perspective. Now I think I'll invite, is it Andrew next, with a perspective on novel ocean observations. Thank you.
Okay, thanks. Can you see my screen?
Yes, perfectly.
Okay, terrific. Okay, so I'll be giving a quick overview of novel ocean observations in the context of where they're helpful and important for tipping points. And as I'm here from the Ocean Ice Project, this will definitely have a Southern Ocean bias and somewhat towards the topics of that project. And now I have to work out.
I think you've muted again, Andrew. Yeah.
Right. Let's fix that. Here we go.
We can see the presentation in presenters mode, not in full screen.
How about now? Is that better?
Still the same. Again, if you wish, I can share it on my screen. And
no, that's okay. This is
yeah.
my fault for using a multi-monitor setup that I shouldn't have been using.
No worries. We're all there.
Here we go.
Yes, thank you.
Okay, now the correct slide. Here, apologies. Okay, so the Southern Ocean is a huge hole in our observing network, and this can be applied into a number of other areas, but the Southern Ocean is something of a really ideal ideal case where it has a very high importance for things like tipping points that have global impacts and a very low level of observability. And that applies to many different parameters. In this case, I'm showing the basic physical temperature and salinity profiles gathered by the global ocean observing network provided by Argo floats. And you can see around the Southern Ocean, there's a real deficit of observations that are available, and particularly close to the coast where the ocean interacts with the ice. This drops down to 0 in many cases. And this matters. So, as I mentioned, the Southern Ocean is disproportionately important when it comes to things like tipping points. And we're seeing some things which are potentially tipping points playing out in real time, looking at the Antarctic sea ice, which has remained very stable over the observational period for the last 40 years, which is shown here. This shows one seasonal cycle from January to January of the sea ice extent. And you can see that most of the observations have been quite tightly clustered. And in fact, up until around about 2016, there was actually a slight positive trend in the Antarctic sea ice area. But since 2016, and particularly in the last year, 2023, and this year as well, 2024, there has been a massive deficit in the Antarctic sea ice area, representing roughly the size of Western Australia, so a very large physical area change. And a number of studies are emerging suggesting that this sea ice actually has undergone a state change in its variability and the nature of it, and possibly the drivers of it, since 2007. But without extra observations, it's very hard to understand the drivers and the consequences of this in more depth. And looking further afield into things that affect global changes, we can talk about sea level rise. So at present, sea level rise is largely driven by steric changes in the ocean, so basically expanding as it warms. But as we run into the future, the contributions of the Greenland and particularly the Antarctic ice sheets begin to dominate. Unfortunately, our current models, and particularly our coupled climate models, don't do the interactions between the ice sheets and climate. And so many of our projections don't really include the impacts of potential tipping point type changes in the Antarctic ice sheet. And so here you can see projections from the IPCC AR6 running out to 2100. And you can see that sea level could potentially change between roughly 0.5 meter and up to 1 meter by the end of this century in many of the different scenarios that are explored. But these scenarios do not include dramatic changes in Antarctic ice and ice shelves, so the potential for collapse and feedbacks of those collapses. And that is modelled, well, it's not actually modelled, it's basically an expert survey, which falls inside this dotted line here, which is potentially up to 1.75 meters, so almost double the model projections. And if you run that out to 2300, that could be potentially 15 meters, which represents significant tipping points and the collapse of much of the West Antarctic ice shelf. So we really need observations of these areas, and particularly observations that are useful to feed our models, that we can then understand how these changes may be occurring and project them. So in the interest of talking about ocean best practices, this is not an area that is unexplored, and many of these organizations exist to basically set best practices for many of the different observations we collect in the Southern Ocean, ranging from physical to biological to ecological parameters. But a lot of these do focus very much on traditional ship-based observations. And as we're finding now, and many of our most novel and interesting observations, particularly of the interactions between the ocean and the ice shelves. So this is 2 pictures coming from Ocean Ice in their recent field campaign. On the left, we see AP-RES. So this is radar sitting on top of an ice shelf. This is the Fimbul ice shelf near the Weddell Sea. Which measures the thickness of the ice shelf and the changes in basal melting. And on the right, we see the now lost, sadly, AUV run by University of Gothenburg that was used to observe underneath the ice shelves the cavity structure. So these observations are absolutely critical for understanding ice-ocean interactions and our ability to model these ice shelves. But they do appear in very bespoke ways at the moment. So they're not really feeding into global data sets. They tend to be data that ends up on an individual investigator's laptop and is often turned into papers. But for larger scale synthesis and feeding in and adjust and tuning models, this is not ideal. Other novel data, so more oceanographic, the preponderance of ocean gliders, which are increasingly being used within and under the sea ice, as you can see in the top left. Argo-style floats being launched in a novel modes so that they actually ground underneath on the continental shelf, which allows them to act as quasi-moorings and allow them to take full seasonal observations underneath the sea ice and in winter, so filling in that wintertime blank with data that can be largely positioned. And on the bottom, this is sail drones. So this is 2 very novel robotic drones, which provide us with air-sea flux measurements, another really important metric for understanding ocean and ice interactions, which is sadly under-measured. But all of these techniques tend to be run by individual investigators or individual teams and don't necessarily feed into wider global networks where we need to compile these data sets and make them more widely available. And this is also in this area of novel ocean observations. A very important feature is that they must be cross-calibrated. So this is an example coming of estimates of the changes in ice shelf thickness, so basically melt rates on the base of ice shelves. And you can see there the Ronnie Filchner ice shelf with a number of observational sites. And those observational sites, I think they're the red crosses, their melt rates are shown as red lines in the various plots on the left, and overlaid on that is the same melt rates estimated from satellite products. And you can see that aside from possibly Site 5, so the middle panel, they are quite different. The satellites have a much higher variability, which is not reflected by the in situ measurements, and possibly reflects issues in the post-processing of the satellite data and some assumptions made about things like surface accumulation rates. But this really underlies the importance of taking these novel observations, not individually, but as a whole. And as part of that, we need to make sure that they are compiled into FAIR, so findable, accessible, interoperable, and repeatable data sets, and make sure that these data sets are not just lost on a server somewhere, that they're advertised. So this is an example, again, from ocean ice, where some of our researchers at the British Antarctic Survey have taken all the available hydrography they can find in the Southern Ocean, so that's the dots on the left, from ships and seals and other platforms, and turned that into sort of gridded hydrography and some climatologies. And they're doing the same with individual ocean moorings, which is on the right there. So these are examples of these sort of the necessary steps to take our new novel observations and make them useful for the community, so that they can perform the sort of simulations necessary to understand tipping points. And again, this is not happening in a vacuum. So groups like the Southern Ocean Observing System, so that's an international collaboration aimed at coordinating priorities, sharing and finding existing data, and forums for collaboration. It's a really excellent example of sort of a grassroots scientific body that exists to really guide and support the scientific community in observations. And as part of SUS, and also supported by Ocean Ice, they're performing, so setting up data systems. So this is an example of SUS Map 2, which is run by the ETT program in Italy. And this is an example of these sort of findable and interoperable data sets. So these data from the floats that Ocean Ice has been deploying, so these green dots are basically being fed in real time into this platform, which makes them very easily accessible by other researchers. So just to finish up, I would note that there has been some really nice recent workshops on talking about these new observations. So how we harmonize different sets of observations. There was a recent workshop that was held in Copenhagen called Recoil, which was looking at validating and reconciling these different observations, specifically of ice shelves. But there will be a new workshop coming up in the coming year, so to be announced, looking more generally at sort of Southern Ocean data sets and how we consolidate these novel observations. So that'll deliver sort of a best practices framework. We can also make sure that the community reaches out and supports integration initiatives such as SUS. SUS is coming to a bit of a financial cliff edge, and that is something that the community needs to recognise if we want this sort of valuable service to continue. And making sure that we extend these sort of delivery platforms to extend such that they already exist, such as the Argo system, to incorporate some of these newer data sets. Argo is somewhat restricted in the data sets it considers Argo, and so some effort could be made to make sure that these new data are added into these existing systems, which are very successful. So I will end there. So thank you very much.
Thank you so much, Andrew. There's actually a question to you in the Q&A panel, so I'll invite you to answer that question either in writing or in our Q&A session. And now I'll invite Hjalmar to share his presentation.
And then I should be on audio, right?
Yes, you are.
And then I'll share my screen. Do you see it? Is it okay?
Not yet, no.
Then we are taking the other screen and we are shown again. Better?
No, unfortunately. But then let me share my screen with your presentation. And
there's so much life in mine, then you're gonna have to do it all the time. So that would be quite unfortunate if you have to do that.
We can't see your screen.
No?
No, nothing yet.
You see absolutely nothing.
Mm.
So this recurs. Did you see my show mode before, or Any other just
No, I don't think so.
So why does this sharing not work for us today? So what do you see on my screen, or do you see anything?
Nothing. We can't see you sharing your screen. Now we do.
You do now.
At least something happened for me. I can see your full screen with the browser open.
Okay. And then
now we can see your presentation. Thank you so much.
you can see it.
Yes.
Nice. Maybe you see yourself also here. Okay. Yeah, I'm Chalmar. This is made by Margrethe. I'm from the Faroe Islands, and I'll take you back up north where Didier gave a nice introduction to this Atlantic meridional overturn circulation, the AMOC, and I'll look at the northern limb of that. Didier showed this to us, convection in the Labrador Sea, producing those deep waters of the AMOC, and the Atlantic waters. So that's a subpolar gyre down there. I'll look more into the Nordic seas. That's the northern part. Where we have these overflows, cold waters that deep flow through the Denmark Strait and through the Faroe Channel, just south of the Faroe Islands there. And this draws these warm waters north, the Atlantic inflow. And the IPCC, as you know, projects that the AMOC will probably weaken during the next 100 years. Some people claim that this might have happened already in the shallower part of the subpolar gyre part in the Labrador Irminger Seas. What I will show is that it has not weakened yet, this northern limb in the Nordic seas. We've been doing measurements along this ridge between Greenland and Scotland, the Greenland-Scotland ridge, where the Faroes and Iceland are sitting on top. As you see here, Iceland and the Faroes, where I'm sitting right now. And these yellow bars or lines show observational sections. Icelanders, Americans, and others have measured it in the Denmark Strait between Greenland and Iceland. And we and people from Scotland and Norway have done so north and south of the Faroes. And then we go out of the ship and measure properties of temperature and salinity, and we put current meters in there, so we kind of keep or check the pulse of this AMOC for these two branches close to the Faroes. And from that, if you look at these Atlantic inflows, 3 branches, the red ones that go north, combine them, we get an estimate of called volume transport, given in the unit of Sverdrup, that's 1 million cubic meter per second. And we see that it's just between 7, 8-ish or so, and fairly steady, maybe increasing, if any. And then the thing that goes the other way, the deep overflows through the Denmark Strait and the Faroe Channel, we also see that that is also rather constant. Has not been updated here, but updates show that this still holds. So there's no trend in the transports, although we heard very much in media how this AMOC is already maybe declining. So not this part, not the northern limb. But the properties, they have been changing, the temperatures and salinities, which I'll show you now. So if you take the temperature in this massive waterfall through the Faroe Channel, this cold, deep waterfall, we can see that the temperatures, they have increased during the last 2-3 decades. And of course, if it becomes much warmer, then seawater becomes lighter, and then there's less momentum to the AMOC. So that is important to follow that development. This could potentially weaken the AMOC. And recently, we also seen some extreme freshening of the subpolar northeastern Atlantic, which we can show you from measurements that we have it's the same all around the Faroes. I'll show an example in this Fairbank channel. This is the Atlantic inflow, the upper waters. And we can see this increase more Atlantic-like. And then suddenly in 2016, we had this massive drop. That's the largest drop we have observed ever in salinity. And again, if it becomes too fresh, then it's also lighter, and density is what we want in order to keep the AMOC running. So these are two major signals in the properties. So my story is actually pretty short. The northern limb is steady, has been maybe increasing in transports, but questions that remain are if this freshening and the overflow water warming could potentially, or if they will continue, and then if they could impact this AMOC. That is actually all for now, but since I have just spent 5 minutes or a bit more, I'll just do a bit of maybe provocation for the discussion, because I also want to say let's not go completely amok or the AMOC. This is an image that went worldwide in the media in 2015. It was El Nino situation. Apropos El Nino, the world was really warm, but we had this cold blobber, and some people claimed, oh, the AMOC is becoming weaker already because this resembled the long-term projections of the temperature of Earth in 100 years from now. And this that's not true. It was really cooling of the subpolar gyre and intensification of overturning, if any. So since then, people have used proxies like sea surface temperature, SST, over the subpolar gyre, and also minus the global temperature. And then they produce images like that, where something goes down. And as I see it, this is, if you take the inverse of that, because you minus the global temperature, this is really much global warming that you see there. So such proxies are not directly valid. They're doubtful, and this has been used as a basis of many high-impact papers that have really gone around in Nature and so on, and media. So let's kind of, it is dangerous. I mean, if the AMOC weakens, it has massive impact, but let's be moderate also in science and media. Thank you.
Thank you so much, and thank you for this provocation. We may come back to it during our panel discussion, which I hope you will also stay for. And now for the last 10 minutes of the presentation part of this session, I'll invite Paula to share her screen.
Yeah, can you see?
Yes, we can. Thank you.
Okay, let's just come back to you because I'm not seeing you again. Okay, so good afternoon, everybody. I'm Paula. Last presentation before the panel discussion here. So I'm talking about from climate science to decision making, how policymakers and financial users can benefit from research outcomes. So I'm a socio-oceanographer, and I work here in Plus Atlantic Collab, which is one of the partners of the OBPS for Clean project. So just very briefly about myself, I was lucky enough to study at university in Brazil, where social science disciplines were part of the oceanography course. So since the first day, we learned that humans are part of nature, and to do ocean science, often we need to incorporate, for instance, the human perspective. So I was happily stung by this concept and following my professional and my academic journey along the topics of the social oceanography. So now entering in my presentation, the first slide here is just to remind us, for instance, how traditional science used to be in the past. So in this old school science, for instance, the researcher was the one in charge of figuring out what was the research question, the methodology, the data you should collect, the observations you need to do. So the focus was mainly in the researcher, the scientist's priority. So science was conducted in this very top-down way, where researchers just assume that once you communicate your results of your work, your findings, the public, the society, everybody would automatically align their decisions with the science. So stakeholders were most of the time introduced later in the process, like often during the communication phase of your project. So the concern of stakeholders, their priorities, or even their local and traditional knowledge were not incorporated into the design of the questions, in the methodologies, in the whole project. So what we used to believe is that, okay, if people had access to good knowledge, a good scientific knowledge, they would make good or correct decisions. But it was definitely not effective in many cases, and you just saw this in the pandemic, in the COVID pandemic, for instance. So a lot of valuable knowledge has been generated, but it was mainly reactive. So we introduce science after decisions are already made. And then, of course, this can lead to a lack of trust in science, just because people don't understand what we are saying, or just because people feel that it's not relevant for them, or even if because they don't agree or have a different view of us. So despite all the amazing progress that we have in the ocean and climate science in the last years, that was amazing, what we were doing was not enough. So mainly if we need to address issues like climate change, biodiversity loss, ocean degradation, which have been escalating, or let's say going down very fast during the last years, this was not enough. So we need to change. So after the decades, we decided to shift from the science we want to the science we need. And we need to change from a reactive science to a more responsive and more transformative science. And then to be truly transformative, it must be inclusive and co-designed with a multi-stakeholder environment. And this is very fun because it makes all the sense. Now, if you are at university or just read a book about that, or go to a workshop that someone is talking about that, to say, wow, yeah, that's it. No, let's work together, people. But this is not that is like this, because many of us, many scientists, we don't have the skills to engage. We don't know how to engage people, or even sometimes we don't have even the desire to engage. I'm here, I'm fine in my lab, doing my things, and I will publish this in an article, and it's fine. But we need to learn how to do that. And lucky of us, in 2021, the UN decided to launch the Ocean Decade. So for the next 10 years, we have a lot of people around the world committed to improve, to strengthen collaboration on research, on innovation, to improve the state of the oceans. So one of the pillars of the Ocean Decade is to become science more transformative and more actionable. A science that is usable, and used by stakeholders. So if you really want to make science effective, we need to make sure that we are working with stakeholders, not in the middle, not in the end. We need to start work with them since the beginning. No, so we need to understand, for instance, the decisions that they are making. We need the challenge they are facing to implement the decisions, and how, for instance, data and how observation, how ocean science could inform those decisions. So the goal of the ocean science is to inform decision-making rather than lead decision-making. So what the ocean science put a light on is the role of science is more to resolve uncertainties and offer feedback, but we cannot impose, for instance, social change or social choice, because it requires more deep understanding of cultural, environmental, political, social contexts. So the Ocean Decade moved towards to this three-part co-design process. So once a common goal has been identified and a relationship has been established, the next step is to co-produce information and knowledge, and then co-deliver the results to our audience. So nowadays we have heard a lot about these two words here, stakeholder engagement. So if you are involved in a Horizon project, in a EU mission project, or in any Ocean Decade action, or any other national, international fund scheme, you probably are aware about the obligation to perform stakeholder engagement activities. And the more the users, we understand that the more the users help find problems and solutions, more the solutions will suit their needs, and more they confident to be to using them. Of course, we don't need to invent the wheel. A lot of people has done engagement activities in the past and also left a good foundation to be continued. So let's take advantage of existing relationships, networks, shared experience. But at the same time, we need to be very, very careful to make those environmentals open, inclusive, and welcome to the new voice. Otherwise, we are going to consult and hear the same people same time. So here is some examples of stakeholder engagement activities, which have been very popular among different projects. There are many others, but I include those ones here. For instance, in my opinion, start with a good mapping exercise, like understanding our audience, their priorities to be involved in, prioritizing playing according to your activities is one of is how you need to start. We also must ensure a very good way to communicate in all the phases, tailoring the messaging according to your audience. We cannot assume that everybody, for instance, speaks English. This definitely doesn't happen, so we need to pay attention to that. Co-design workshops, webinars also is a good environment to put people together to discuss. Sometimes a very nice and ludic participatory way to discuss with people. Public consultations, such as, for instance, surveys, have been widely used. Is a quick way, to engage and collect requirements, but you need to be very careful on that as well, because if every single project has a survey nowadays, several projects share the same stakeholders, definitely we are going to overload our audience, and you don't want that. Policy brief events are very welcome as well, has been just highlighted by one new report released today by the Ocean Decade. And I would like to mention also the power of the community of practice has been very used in these mission projects, where you have these community-led pilot actions, where a group of people who share the same concern, the same problems, the same views, they work in a collaborative way to put actions in practice and learn how to do this and how to do it better, for instance. And being more specific for OBC for Clean project, that we have a work package dedicated to stakeholder engagement, led by the coordinator of the project by the DMEI, but with the support of the Eurogoose and the Plus Atlantic, now in this case myself. We have 2 tasks dedicated to stakeholder engagement. There are many activities inside these 2 tasks, but today I would like to mention, for instance, the setup of a stakeholder reference group, where we already did a participatory method exercise with the whole consortium to really understand, for instance, who are the people essential for the development of the project, people who need to be consulted, and those, for instance, just need to be informed. We had also planned, for instance, policy events, including the reference group, of course, in those events, but in this case, to co-design and co-produce recommendations to policy implementation and also policy monitoring. So my last slide here, I would like just to leave a message here about also the dangers of the poor stakeholder engagement and how serious we need to be when planning it. So we need to be careful with engagement activities only performative. So when stakeholders are included only by name, without real influence, without a real decision on the process, just because it's mandatory. So let's do a workshop, that's it. We need to just be careful with poor communication or a lack of follow-up with the stakeholders during the phases of the project. Mismanagement expectations is essential. We need to be very honest with what we are going to achieve and how we are going to use the information collected. We need to be careful with the exploitation of resources. In this case, I'm talking mainly about time. Everybody nowadays have a full agenda, so time is very, very priceless. We need to avoid stakeholder fatigue. So if we're going to run many consultations with the same subjects, we need to be more collaborative among the projects to avoid that. And normally, last one, we normally don't do a stakeholder success evaluation assessment. The project finish, and you do not assess how good or how bad was the engagement. We just move on. So we must learn with our mistakes to make sure that the next time we will make science more actionable for policymakers and users. And just to finish, we need to have this in mind, like the science becomes more effective only when stakeholder trusts the data collection, trust the analysis, trust the conclusions of your finding, which is why the involvement of stakeholders is crucial since the beginning of the project. So that's it. I think it's okay. Thank you very much.
Thank you so much, Paula, for leaving us with this important message. And thank you to all the presenters for excellent presentations. I think they all gave us some insights on different aspects of the Ocean Climate Nexus. Now we'll move on to the Q&A session and the panel discussion. Unfortunately, Laura Jackson had to drop off of our panel. So formally, we are here with Juliette Mignot, with Didier Svingado, and with Ana Oliveira. But of course, I also hope that other presenters who stayed on in this session will join our dialogue and discussion. So if there are any questions from the audience, I very much encourage to write them in the Q&A box, and we can then address it in plenary. But maybe I will start with asking a question. I would like to maybe ask Juliette a question, if I may, on how we discussed today quite a bit about the importance of observations, and I was wondering if you could maybe round off this discussion and the different presentations, the different discussions that we've heard here today on how important are observations for modeling of climate tipping points, and maybe also reflect on what is the role then of past observations and reconstruction for understanding tipping points.
Yeah, thank you very much, Justina. Thank you everyone for your talks. Thanks for the question. Perhaps I'll start with the second one. I think today we've heard a lot about current observations, and I completely subscribe to everything that was said about making our best to sustain observation systems, to develop novel observations, to make the best, I mean, to try to understand, to calibrate, to debias, to maintain the observation system. I was almost, I would say, yeah, I was, it was very nice to see the observations by Hatun, which I discovered, in fact, as I was a young PhD student. We had the first points of these observing lines. And in each project, yeah, when I was attending projects, I think together with Didier, we could see each year one more point. And now we are, I mean, it is a very nice 10 or 20 years later to see what we can say about trends. So this is crucial. Yet, I think past observations are also important, and reconstructions and trying to have indirect observations of the past climate is very important for tipping points, because precisely for tipping points we need a temporal background to try to investigate first a sort of a background state and background variability on which we can test whether we are reaching a tipping or not. That's one thing. And also, if we have a large temporal background, we have more chance to observe or not tipping points which remain fairly rare events. So I wanted to stress that here in this discussion. And shall I move on with your second questions, or perhaps other panel members have reactions about past observations? I don't know. Nope. Okay, and if not, I can go on with your second questions, which was, I think, how important are observations for modeling climate tipping points. As Didier, I am a climate modeler, so I don't maintain any observing systems. I don't go at sea. I am a dry fit oceanographer, as we say in French. Yet, I think these observations are crucial for our work as well, for modeling, because we need, of course, to calibrate our climate models, and we need really to understand the range of uncertainty that in which our model may move, may lie as compared to observations, and this is crucial. And of course, tipping points in the current years are, I mean, in the past years, and hopefully in the coming years, will mostly be modeled, and I hope, I may be wrong, that they will be modeled before observed. But in order to identify them, then we need to know whether we are still in the range of observations or not. So I also wanted to stress here that for climate modelers, observing tipping points is crucial.
Thank you, Juliette. Yeah, I think Didier also mentioned in his presentation that while we do have huge uncertainties in the models, then using observations can help us with reducing this uncertainty. And Didier, you mentioned specifically this multivariate approach that you've been using. Out of my curiosity, is this approach something that's known in the climate modeling community, and is it something that could be considered also best practice in addressing uncertainties in climate models?
Yes, that's quite a new approach, in fact, quite empirical, to be honest, and but you have some ways to test your method by taking one of the model as a true observation and testing if with the knowledge that we have over recent days, we might say something about its future, and that's the validation approach that I have shown, but it was a bit fast, and it's working reasonably well. So if we can believe this approach as a validation, it seems that it's working. Then it has been mainly done with one variable, one predictors, meaning that you take one of the variable and you say that it's representing a process that is explaining mainly the spread among models for climate sensitivity. That's where it has been used mainly at the moment. And in fact, you can question that because, of course, we know that climate is quite complex. Climate system is very complex, and so it's quite unlikely that just one process might explain all the uncertainty in models. So using multivariate approach might be relevant. Then the risk, of course, is that to have overfitting, to find some variables that explain pretty well the spread, but for wrong reason, just by chance. Once again, this can be tested also through a statistical approach, and so we've done that as well. And last, validation, of course, is a kind of physical understanding. When you find your kind of variables that explain the spread among models, you might try to interpret them and find a way to relate them with some well-known processes. And so, yeah, in the example I've shown, that's what we have done more or less. And what we found, we end up on variables that are already in the literature, and we haven't cheated. So that's something that was real. So that's quite interesting. And that's only the infancy of the method in a sense. So we used surface variable at the moment, but in fact, there is no reason why not using, for instance, the data from Hjalmar as shown about the overflows. It's more work to diagnose that in models, but strictly speaking, you can really use as many variables as you want. And what you need also to consider well is the uncertainty in the observation. And that's where also I have some depths, I should say, because for instance, we used here EN4, and from time to time, the uncertainty that is provided is from time to time a bit small. And also when you average, you might think about what it means in terms of uncertainty, and this is not very clear. So there are still some work to be done there, but strictly speaking, there is no reason why it should not work well. And the consequence also is that you might need as many models as possible, because you're working here on the dimension models. And so with 32 or 40 samples, so this approach argue in favor of continuing to have a diversity of models and not pushing all our effort on just a few very high resolution models, because we have no no security that it will solve everything. And first tests have shown that, in fact, two high-resolution models can still show very different response. So it's not solving everything. And the diversity of models might be a way to move forward. But we really need, even though we go multivariate, we really need to keep something that is understandable. And that's the risk with because this is statistics, so we can push as much as we want using machine learning approach, even though something is too small for machine learning. But anyway, but if you don't have any interpretation at the end, that's where care should be used.
Thank you, Didier. Juliette, did you have a comment to it? Or a follow-up?
Yeah, it was just a small comment too, but then Didier went on. But I just wanted, I mean, something also that I would like to take from today's presentation, and Didier very nicely illustrated this point, is sometimes the difficulty for I would say climate modelers and climate analysts, I would say, to integrate the most recent data in our analysis and in our constraints. I mean, Andrew has shown that very well, and it's the same for Halma. Perhaps it's always frustrating for us that we have all these data here, and it's a huge job to integrate these data in some like easy data sets that we modelers can use and which our models can ingest. And so there is a gap here that would be nice to try to fill, because we really need these measurements like the ones that Halma has shown. And of course, I'm also thinking about the rapid data. Laura left us, but she would probably have mentioned it. And that's really something a message I very much appreciated in Andrew's talk.
Thank you, Juliette. And I'm glad you also mentioned the topic of data, because I think when we've heard so many times today on how much data, different data types and coming from different sources is collected to feed into these different experiments and simulations. And they do come in different formats and standards. So I would like to maybe ask Anna to weigh in here on this challenge of managing these amounts of data, and maybe you could reflect a bit on what do you see as the main challenges for ocean observation best practices moving forward in relation to data.
Thank you, Justina. So yes, indeed, I think this is common to all kinds of physical observations and direct observations in general. But mostly it's a challenge for those like we at Plus Atlantic working with remote observations, because remote observations are always a function of the in situ observations that we have to calibrate, validate whatever modeling we apply to the radiances we see from the satellites. So in this sense, the in situ observations, direct observations are a must-have that unfortunately I think it's not enough emphasized due to this like overload of AI, geodata science, modeling, etc. It's not that those are not important, not at all, including this is what we work the most, but we always need to have ground truth, and this ground truth to be standardized, reliable, so that we can do some benchmarking across models, across techniques, and have our, let's say, fit on the ground. I think WMO and also GOOS have done a very pretty good job in putting together the essential ocean variables and essential climate variable standards. These are, I think, the way forward in terms of having reliable quantifications of the accuracy, the targeted accuracies that are desirable for each variable, regardless of the observation strategy. There's also the question of the confidence interval, because average accuracies are not enough. And one of the things that I worry about, especially in SST extremes, marine heat waves, is that sometimes the overall accuracies and the average accuracies and the metrics reported at the data set level do not reflect the accuracies in the extremes. And this is very important because relationships sometimes are not linear in terms of the correlation among the observed remotely and in situ variables or the models. And we tend to underestimate these extremes, especially heat extremes, as we are seeing with climate change. And when we talk about marine heat waves, especially, we need to have this kind of best practices also reporting the accuracy in these extremes. But to go that way, then we would have to have also standards for the extremes detections, because otherwise we are not comparing things that are comparable, like what's the percentile, what's the climatology. All of these things have to be taken into consideration. And yeah, I think there is a very good job done so far, and probably the next steps is to further consolidate these best practices, also to include the extreme observations as accuracy standards as well.
Thank you, Anna. I wonder if I can direct a question to Andrew. I know, Andrew, that you're not maybe formally part of the panel, but I think that what Anna was saying maybe relates a bit to your presentation that you've mentioned there, the source system, and then the work that they do on capturing different data streams and sort of categorizing them with these FAIR principles. Is there something that relates here to these best practices and standards for the data management?
Yeah, so I mean, they typically adopt best. I mean, the observations themselves are made with best practices that are set by groups like Goose or the GoShip panel. But in terms of actually long-term curation, I think, yeah, so the SUS data portal is a really good example of this consolidation process. But I mean, it is still set up very much in a grassroots sense. So SUS is a body of SCAR, but most of its funding really comes, particularly for the data aspects, has come from individual projects. So for SOCHIC, really got it started, I believe. That's a Horizon 2020 project, and Ocean Ice has carried that on. And so while they exist, and they are providing really valuable services in consolidating these data sets, it doesn't really represent a larger scale approach to things, where things like the WMO or the Argo program, which are sort of very large processes, multinationally funded, represent the gold standard. So I think what we need to do as a community is really identify those products that we would like to see elevated to that level, and really make a concerted push for the adoption of new observations such as these bottom landing profilers, or new techniques such as the APRES, for example, in the Southern Ocean sense. I'm sure many others exist in different areas, to really have these sort of incorporated into these QC'd long-term funded data centers, because otherwise things like the SUS data portal will eventually run out of funders. I mean, we very much hope that ongoing projects will continue to fund that, but eventually it might just become orphaned. So we need to make sure that there's this pipeline that recognizes the importance of emerging data sets, consolidates them, and then ultimately gets them made into operational by these sort of very large multinational groups. So I'm not sure if that answers the question or if I wandered off topic there, but that's...
No, all good. Thank you. But then maybe in that light, I'm also wondering if, and that's a question to broadly to the panel and the participants here, what is then the relationship between efforts like this and the ocean best practices system? Is there some sort of potential for support or connection, or submitting some of the best practices so that they do live on also in OBPS format, let's say?
That's a good question. I don't think I'm really the right person to ask that question. I'm not as familiar with the Ocean Best Practices framework. So, but I mean, I'm sure people like the people who curate this, such as I mean, those working in ETT, like Antonio Novello, or even Copernicus, would have a much better opinion here. So maybe I'm not the right person to comment.
No worries. But then maybe broadly to the rest of the panel, if anyone has more experience in this connection, let's say, with OBPS or generally working with the best practices in ocean observing. What could be the potential support from organizations like Ocean Best Practices to link to, also support the science on the climate tipping points? Juliette, do you have a comment?
Yeah, it's just a comment. Of course, I'm not going to answer. You all understood that I am not the one really involved in ocean observations best practices, but I would like to highlight that from what I see and from what I discuss with colleagues, none of the great observing systems that we've been looking at today and discussing today have long-term funding. There are people there fighting every day, every week, every year to have the funding. So I think one of the best practice that we could have, or if an organization like OBPS could help, would be really to support longer term funding so that these people could concentrate on developing the observing system rather than fighting for funding. And my illustration about Halmar's data earlier on is really that at the beginning of these observing systems, you say, okay, that's nice, we have 2 points, it's really fun to observe the overflow. And then 20 years later, you come and then you have this long-term trend and you realize that, I mean, thanks to a daily or a yearly effort of these people, there is no hole in the time series. Of course there is, but like on the yearly average, there is no hole, and that's just amazing. And there is no way you could go back. When I miss a simulation or I forgot to make a simulation, I can always rerun it. When we miss 1 year or a couple of years in these observing systems, you can't go back. So that would be my message.
Thank you. So if we think of a good observing system for tipping points, do I understand that we need to ensure its continuity? But what are there any other qualities of a good observing system for tipping points? That's the last question and an open one to a panel, if anybody would like to reflect on it. Yes, Shalmar.
Yes, thanks. Yeah, I think we should. It's nice that we have these observations in key flows, and I think we should continue to do so. And it does not require all the, it's called ADCPs, these current instruments that are in there. We have a lot of them, but we can do it with a few located in key positions. Because now also products from Copernicus, like ocean reanalysis, they can actually start to reproduce the same series that I showed you. So I think it's important that we stay in the core in order to work with Copernicus and also to do it together with them, because if I validate their ocean reanalysis, they are good in places and they're bad in places. So to do it together with them and to be guided and feel where are the weaknesses in the ocean reanalysis, always stick to the main course, but in that way observe more cleverly in the future.
Thank you. Any other inputs on a good ocean observing system or observing system for climate tipping points? Yeah, Juliette.
Yeah, Didier has mentioned uncertainties as well. I mean, it's good that we, and this is what I meant also when I was mentioning that we need to have a range both of natural viability but also we have to know the uncertainty of the data, at least from my perspective, which is trying to test to see from what point does my model get out of the natural variability and possibly simulates a tipping point. I really need to have an idea on how robust my inference are and how robust the observations are. So having uncertainties associated to each measurement is pretty important, I think.
Duly noted. Thank you, Juliette, for the inputs. We are 1 minute away from the end of today's webinar. I think we are left with some good food for thought in terms of ocean observation and its relation to studying tipping points. Thank you to all the panelists and all the presenters. I think this was a very interesting session. it lives on, so it will be it's recorded and it will be accessible on YouTube. So if anybody would like to share it or get back to this session, you are very welcome. And please also remember to connect with our projects. And I think all of us remain open for any questions and I don't know, potential for engagement. But thank you so much for today. I think we'll leave it at that.
Thank you.
Thank you, Justina.
Thank you, Justina. Thank you,
Thank you.
everybody.
Thank
Thank
you
you,
all.
Tanya. Bye-bye.
Thank
Bye.
you. Have a nice evening. Bye.